Those who are online, are you able to hear me?
Yes, sir.
Those who are online, are you able to hear or not?
Yes, sir.
Yes, sir.
The previous chapter, right? The previous chapter, right? So the previous chapter, that is under ray optics, right? So if you see, the branch was classified under optics itself, right? So what is optics all about? Optics is a branch of physics which deals with the interaction of light with different kinds of objects, right? So when I say interaction of light with different kinds of object, when light falls on another object, it exhibits different kind of phenomena, correct? So what kind of phenomena did we see? One is reflection, then we saw refraction, then we saw. So basically we saw the concept of reflection and refraction, right? So apart from that, light can also exhibit different kinds of phenomena named as interference, diffraction, and polarization. Okay. So here comes an important concept to be defined. That is, you take optics. Yes, I'm clear with the fact that optics is a branch that deals with light and its behavior. Okay, excellent. Then why are we classifying the optics into two branches? That is, why are we classifying it as ray or geometrical optics or something called as wave optics? So that is dual nature. But in both the cases, light is wave only. So whether you discuss about light in the topic called as ray optics or wave optics, the point I would like to mention here is, in both the scenarios, light is behaving like a wave only. So, because when you talk about refractive index, are you not relating it to wavelength? So, if it was a particle, where will a particle have a wavelength associated? That is right. Yes, you actually see it as a macroscopic thing. But if you see the previous chapter, in the beginning, I would have given a point stating that it depends on the nature or the size of the object with which light is trying to interact. If the size of the object with which light is interacting is more, then you treat light as a ray. Whereas, if the size of the object is comparable to the wavelength of light that you're using, right, then you treat it like a wave. So one point I would like to correct here is what you told is right. Light has dual nature. When I say dual nature, what am I trying to talk about? I'm trying to say that light has wave nature and particle nature. But for your information, I repeat it again. both in the 9th and the 10th chapter, we don't discuss about the particle nature of light. In both the scenarios, it is behaving like a wave only. So, where does it start behaving like a particle? We will see. Okay. So, I'll start getting into the chapter. So, what is wave optics? The first point, if I have to say, it is a branch of physics where light interacts with objects. Size is comparable to the wavelength of the light used. Right. Generally, when you talk about the light here, what kind of light are you talking? You're talking about the visible light, right? So for visible light, what is going to be the wavelength? The range of wavelength is somewhere between 400 nanometer to 700 nanometer, or 450 to 750 nanometer, approximately somewhere. Right. So when you say nanometer is generally 10 power minus 9, which is a very, very, very small. Right. So if you are able to think of an object, size is approximately in terms of nanometer, it is then you can classify light as a wave. That is, you classify or you treat light like a wave and start exhibiting the properties of waves associated. Okay. Or I can say start applying the properties of waves to light. Is that clear? So before we start discussing the different topics that are there in this chapter, we need to first discuss the concept of nature of light. So if you go back to the past, right, there were different theories that were proposed at different points of time. Right. So initially, the theory that was proposed with respect to light was corpuscular theory. Okay. So there was a theory that existed which was called as corpuscular theory of light, and it was proposed by Newton himself. Right. So this was proposed the year 1675 AD. In this scenario, what we told is based on different kinds of observation. Basically, if you see science, what are we doing? We see something around us, and we try to give an explanation. Good, right? At that point of time, what happened is based on the way light was reflecting and getting refracted. So Newton started framing a theory. He started saying that light behaves only as a particles. So basically, corpuscular means particles. So what he suggested is that light consists of tiny particles called corpuscles, right? Which are shot out at very high speed by luminous objects. Suppose this tube light is there. This is a luminous object. He tried to say that this object is shooting out tiny particles called corpuscles. What happens to those tiny particles is they go and fall on a particular surface and reflect by undergoing elastic collision. So you know what happens in a perfectly elastic collision? The momentum is conserved in the sense whatever speed with which the particle goes and hits the stationary object, with the same speed it will get bounced back. So based on which he tried to give you the concepts of laws of reflection and the refraction. Okay. So this was a theory. So this theory could explain the phenomena such as reflection, refraction, and rectilinear propagation of light. Because this was observed at that point. Okay. Later came the concept of wave theory of light. So after 3 years, I can say what happened is in 1678. So there was a Dutch scientist named Christian Huygens. Okay. What he started proposing is he suggested that light does not travel in the form of particles, rather it starts traveling in the form of waves. But here comes a twist again. So today we know that light is transverse in nature. But when he proposed it, he told that light travels in the form of longitudinal waves. Okay. So these are all theories. I am not saying they are right. At different point of time, they were corrected. Okay. So in the form of longitudinal waves, like how like how sound propagates through air. He also told that that light waves propagate through all prevailing hypothetical media called luminiferous ether. So he called those media as luminiferous ether. So luminiferous means it is derived from the word luminous. So the objects which are actually allowing the light to pass through them. So if you go back to the story, right, why did he think that light traveled in the form of longitudinal waves? I'll give you an example. Suppose this is the window of a room. Okay, this is where I keep my hand. let's say here there is sun, or here there is some luminous object. So when light falls from here, right? Let's say I have a circular object in my hand. When that circular object's light is falling on a screen, what kind of an image is supposed to get captured? So if I have a circular object, right, I give you a ball. Let's say I dip that ball in a grease and give it to you, you throw it on a wall. What kind of a patch will you find on it? You'll find some patch of grease that is there, which is circular. In a similar way, imagine that light is also falling. Okay, then what kind of image are you supposed to find for a circular luminous object that was placed? You should have found a circular thing. But what happens in reality, for example, if that would have happened, right, it would have not survived in today's world. Not only in today's world, at any point of time, light would have been used as tools. Because what happens? Let's say you have such a big house, but if you see the size of the window, it is small. So when light is coming, if the window is open, what happens? Light falls and it starts scattering. And see, if you take the window to be in a rectangular shape, let's say there is a wall exactly opposite to the window, then what should have happened? Light should have been present only on the opposite wall. But is that what happens in reality? No, right? Your room is lit up. See, intensity, that is a different story. But the fact is, light is able to get scattered. So here comes a question of who will be able to exhibit this kind of a phenomenon. So what he tried to do is, he was actually trying to contradict the corpuscular theory, because what is proposed in corpuscular theory was particle. Had it been a particle, through this hollow space, if the particle is traveling, the particle should have traveled without any deviation. It should have gone and hit the wall. But it is wave that can exhibit the property of scattering. So that is why what he did is, he tried to compare light exactly with that of sound. So if I have to give you a better example, okay, let's say this door is completely closed. Okay. Let's say there are two people sitting here and they're fighting. Okay. And you're here and you're casually sitting. Okay, they are shouting at the top of their voice. If the door is thick enough, okay, so that it is able to cut the sound that is traveling from one room to another, will you be able to hear? The door is thick enough and it is soundproof to nature. Okay, let's say it is soundproof. Will you be able to hear what they are speaking? But if the same soundproof door, if I open it slightly like this, will you see it at this point? If it is slightly open to this extent, will you be able to hear? Yes. Why is it happening? Because sound, after it hitting the interface, it is getting scattered or it is getting diverted. This kind of a phenomena is basically called as diffraction. You're able to understand? So this cannot be exhibited by particles, it can only be exhibited by waves. So this is one of the examples that we tried to put at that point of time to say that light had wave nature, it didn't have particle nature. But people didn't accept. That's a different story. Look at the time gap. 3 years gap and nobody will be ready to strike off Newton. He was a very big scientist at that point of time. People didn't even believe. So that's what happened. But he proposed a statement and it was killed. Later what happened is, this kind of a medium, this luminiferous ether is there now. Later on, the existence of such media was discarded due to its contradictory property, because light can travel even without a medium. You don't need something like that to be defined. So that was not there. But fortunately, later what happened is, there were two scientists named Fresnel and Young. They were the first people, right? They were the first set of people to prove that light had transverse nature. Because they proved light had wave nature by doing a small activity. And that activity was called as interference, about which we'll be learning in this chapter. So they were the first, we call it as Young's double slit experiment, which mainly speaks about the concept of interference of two waves. Interference means, you know, that when two light waves are falling on each other, they undergo superposition and some resultant intensity is observed. I'll show you everything in the form of a simulation. Okay. So they told that light propagates as a transverse wave. This successfully explained the concept of. So even with wave theory, what they could do, they could explain the concept of reflection, refraction. In addition to that, they could also explain the concept of interference, diffraction, and polarization. So that is when, after looking at this property, they started believing that light also had wave properties. Now what happened is, the particle nature was discarded. Because here you have put something. So unfortunately, what is happening? Here they could know only reflection, refraction, and rectilinear propagation of light. But what is happening in the case of wave? In addition to already proven properties like reflection, refraction, we are also able to prove three other additional properties like interference, diffraction, and polarization. Right? So they started believing that light had wave nature.
Sunlight, suppose the wave is sunlight is because got crystals from sun.
That's what you mean. Right. So sun is a luminous object, and luminous object is releasing particles. Had the particles existed, right, they would have actually struck us. So already, if you see in today's world, electromagnetic waves are causing a lot of factors. That's why they say you should not have your mobile phone in the pocket closer to your heart because of the radiations that are coming. Yeah, that would have happened. Right. It is going to hit, right? You would have found some holes also. That is going to damage, right, at the end of the day. Right. Because they are not coming in terms of one or two quantity, it is going to be in terms of billions of units. So that didn't work out. But at that point, he tried to propose a theory because his main work was in mechanics. So he tried to relate light also to mechanics and give an explanation. Okay. So with the end of the slide, we understood that people started believing that light had only wave nature, but that is also not true in today's world, right? Then came the concept of electromagnetic nature of light waves, which was discovered by Maxwell in the year 1873. He suggested that light travels as electric and magnetic field oscillation, where electric and magnetic fields are mutually perpendicular to each other, at the same time they are perpendicular to the propagation, the direction of propagation. That is where the concept of transverse wave also comes, right? So these waves were called as electromagnetic waves, which require no medium for propagation. We know it today because it is a non-mechanical wave, and these waves are transverse in nature, right? So I told you the concept of polarization, right, in the previous slide. So polarization can be exhibited only by waves which are transverse in nature. Longitudinal waves cannot exhibit. Why is it so? We'll see it at that point. Okay. And the next theory that came was Planck's quantum theory. So generally when you say quanta is basically a packet of light energy, right, which we call it as photons, right? So according to Max Planck, light travels in the form of small packets of energy, and they were named as photons. Okay. So with the help of Planck's quantum theory, what happened is in 1905, Einstein used this theory to explain the concept of photoelectric effect. So you know what is photoelectric effect? Let's say I have a metal surface, right? So generally we target only metals because metals have usually bound valence electrons. So when light of sufficient energy is hitting the valence electron, what happens to the valence electron? They get knocked out. So according to electrostatics, if an electron is lost from a material, what happens? It gets positively charged. Basically, it gets charged. Right? Electrons play an important role. Either you add them or remove them. But in the case of photoelectric effect, name is suggesting, see, photo refers to photons, electric is charge, and effect that you're able to observe. So that's why you call it as photoelectric effect, which is basically emission of electrons on the metal surface when light falls on the surface. Okay. So this theory of photoelectric effect could be explained only using particle nature of light. So what happened? Thomas Young and Preston together, they explained the concept of wave nature of light. Then in this year, electromagnetic nature of light waves is also supporting the wave theory. But what happened in the year 1905? When the concept of photoelectric effect came into picture, when the explanation was given about it. So phenomena was observed. See, the phenomena was observed even few years before itself. Okay. But we need to give a scientific explanation for someone to believe it. Right? So in the year 1905, when the photoelectric effect concept came into picture, that is when people started believing that light had both wave nature and particle nature put together, which we combinedly call it as dual nature in today's world. Are you able to understand? 1905, almost 160 years back, 170 years back, right? So are you able to understand? is what the theory of light is. This is how it started. So in this chapter, we are mainly going to restrict ourselves to the concept of interference, diffraction, and polarization. So with respect to CBSE, polarization is removed. Okay. But it's a simple concept, only time permits, I'll explain. Okay. But interference and diffraction, we concentrate. Before that, we need to have little more understanding of wave theory of light. For that, let us take an example to understand. So for you to understand the concept of wave theory, the first term that you need to know is called as wavefront. Okay, wavefront is not a very big concept that is so confusing or something. This is something you already have observed in a different medium. Okay. For example, there is a still water. Let's imagine there is a still water. And if you take a small stone and drop it, once the stone goes and hits the still water, what is that you will be able to observe? You will be able to observe a set of concentric circles being formed. Right? So the set of that concentric circles, you technically call them as ripples. Right? So what they actually do? So how is ripple formed? When you see it from different view, you have a different perspective. When you see from the top, generally, that is what we do. We generally do not go under the water and check it, right? So, but what happens? Water has elastic property associated because the particles are loosely formed. So, something which is elastic only, it will be able to exhibit this kind of a wave property because they need to undergo vibration. So, it needs to be an elastic particle. So, if suppose this is the water surface, okay, as soon as the stone, let's say my knuckle is the point, okay, this part. So as soon as it is going and hitting the knuckle, what will happen to the water particle present in this region? First is, can I say that the water particle will first go down? Is it not disturbed from its equilibrium position? Am I right? Are you able to visualize what I'm trying to say? So it is disturbed and it starts vibrating. So it starts vibrating about its mean position. So mean position is the point where I created the disturbance. So it starts vibrating. But how is it able to form the surface? That is an important question. So it should have vibrated only in its mean position. Then what is happening? So it is not disturbed only in this direction. It will get disturbed in the horizontal direction as well. So this vibration, what will happen is it will start transmitting its energy to the subsequent particle, as a result of which this will lose its vibrational energy and slowly come to rest, and the particle next to it will start attaining more vibration. As a result of this, the energy is transmitted from one point to another. If you see, what is the main objective of wave in the first place? Why do we need a wave? So wave's main purpose is to transmit energy from one point to another. You can do it either in the form of making it travel in the form of a longitudinal wave or a transverse wave, depending on how you are going to vibrate the particle or how it is happening naturally. That's a different story. But if you see in the wholesome perspective, it is like energy is getting transmitted from one point to another by creating some source of disturbance. So wave is basically a disturbance that carries or transmits energy from one point to another in the form of propagation. Right? So suppose a stone is suppose a stone is thrown on the surface of still water, you can see circular patterns of alternate crests and troughs. So generally, you know how longitudinal waves travel, right? How do they? Suppose I'm speaking, okay, I'm turning this side and I'm speaking. Let's say you have some device in your hand which is able to capture how the how the air particles are able to. Let's say I give you a camera which you're recording in slow motion or something which is able to capture the air particles. How will it travel? So I'm trying to compress the air particles here, which in turn is trying to expand the air particles somewhere else. Right? So sound travels in the form of longitudinal waves, which mainly undergoes the concept of compressions and rarefaction. Right? But here we are trying to speak about crest and trough. So where does it appear? It appears only for a transverse wave. So here comes an important point. When we see circular particles, right? If somebody puts a question, you will start thinking that the water ripples are actually longitudinal in nature. They are actually transverse. Okay. The water particles actually undergo this kind of a vibration where you have crest and trough. What do you mean by crest? The top part. And trough is a bottommost, right? So they begin to spread out from the point of impact. Clearly, what you can say, all the particles lying in the crest are in the position of their maximum upward displacement. Suppose, so let's try to visualize the diagram. So I'm saying that when I see from the lateral view, let's say there is a water surface. Okay, when the stone falls from here, from the top point, you will be able to see the circles. Whereas from this side, what will you be able to see? You can see that the elastic medium is vibrating in this way. So energy is transmitted in this direction in the form of circular rings, and the vibration takes place in this direction. So they both are transverse in nature. They both are perpendicular nature, etc. Right? So when this happens, right, when I see it from the side, that is in this view, like how you give us, like when I see it from this view, what will happen is I'll be able to see these kind of waves. Right? So when I say these kind of waves are defined, then the topmost point is technically called as a crest, and the bottommost point is called as a trough. So what they're trying to say is, read this point. Clearly, all the particles lying on the crest. Right? Here there is a particle. So here there is a particle. Here there is a particle. Here there is a particle. So there are multiple particles throughout the wave. So all the particles lying on the crest are in the position of their maximum upward displacement. More than this point, focus on this word. And hence, can I say that they are in the same phase? You know what is phase? Phase is basically the angle which corresponds to the motion, which we measure in terms of radian. I'll come to that story, okay? So, but I hope this point is getting registered in your book. Are you in agreement or not? So they are the same maximum height and they are having the same phase as well. Okay, this word phase is important, remember, for you to understand what is the effect. Similarly, if I talk about all the particles which are lying at the bottommost point, I can replicate the same explanation. Right? Similarly, all the particles lying on earth are in the position of their maximum downward displacement, hence they are also in the same phase. Right? Comes an important question. If I join all these particles, right? If I join all these particles which are vibrating in the same phase, then I get a shape. And that shape is generally called as locus. How many of you have heard the word called locus? L-O-C-U-S. It is actually a mathematical term. So what is locus?
Focus of the locus of points.
So locus point is basically a moving point. Okay. See, suppose you know how the compass is going to look like, right? So let's say this is the pen and this is the tip of my compass. If I keep my compass fixed at a position, what am I actually doing to the pencil? I'm revolving it, right? When I revolve it, can I say that this pencil is creating multiple dots closer to each other that you're not able to differentiate? So the multiple dots are created close to each other, which looks like a continuous shape. And that continuous shape is what you call it as a circle. So in this scenario, you call it as a circle, but mathematically speaking, you call that kind of a scenario as locus of all points. Locus is the shape obtained by those moving points. So similarly, ellipse is also a locus. Hyperbola is a locus. Parabola is a locus. Straight line is a locus. So you just try to define it. Like how you will say is, if I ask you how to define a straight line, you will say straight line is a locus of all points which are collinear. So what is collinear? Basically something that lies on a straight line. You are just giving a different definition, a reverse definition. Similarly, how do you define circle as? Locus of all points which are equidistant from a fixed point. Similarly, how do you call a parabola as? Locus of all points which are equidistant from a fixed point and a fixed line. The fixed point is called as a focus and the fixed line is called as directrix. So similarly, we keep going like that. In a similar way, in physics, what we are going to do is we are going to take that locus point. Suppose there are multiple waves like this, okay, where I take the position, right? I take the position of rest. So if I join all those positions, then I get a locus. So this line is there, this line is called as the locus. So locus of all points, listen to this carefully. Look at that, the shape obtained by joining all the points which are vibrating in the same phase is what is called as a wavefront. Repeat it. Wavefront is basically locus of all such points. What points? All the points which are in the same phase. It need not be crest orbits or it not be trough orbits. If you choose a particle which is in a particular phase, you need to choose a particle on the other wave also which is the same phase. And you join everything and you obtain a shape. And that shape is given a name called as wavefront. It's not a wave, it's a shape of a wave. You have, see, wave has a diagram, but wavefront varies depending on what kind of a source you're using. For example, if you use a laser light, that has a different wavelength. If you use an emergency light, have you seen the emergency light which looks like a tube light and you hold it whenever there is a power cut? Have you ever seen one? Right? You charge it and have it. So that is, see, for example, tube light is there. Tube light is not a point source. It is a linear source. Similarly, I can think of a source which is at infinity. Are you able to understand? So the source which is at infinity is relatively a point source, but it is not a point source. For example, if the same light is there, I am trying to stand at a greater distance. With respect to my position, this is acting as a point object. So I cannot combine point object and the object based at infinity. So these are the three different scenarios according to which you have three different wavefronts. I'll discuss that. But I want you all to register this point of what is a wavefront. Can you all define? It is a locus.
So locus really exists. It's not really exists like particles in the same space. Only one.
Yes. No, I'm saying you wavefront is obtained by joining all those points. It is not like wavefront is existing only because of that. Wavefront is obtained by joining all those points which are in the same phase. I'll explain it to you. It's not wave. Wave will not have multiple waves. Source will have multiple waves. So
this wavefront for this wave, which is drawn.
this is wave term. Okay, this is a wave.
Is the
This
wave-
dotted line is the wavefront.
But wouldn't it be straight line or something?
That is, you have to see in this direction. It will be like a plane. That depends on where the source is. I generally do random waves. I didn't tell you what kind of a source I'm trying to talk about. I only try to explain what is the meaning of locus of all points. Yeah. I'll come to the point. I'll come to the reason for this. So the locus of all points which are oscillating the same phase is called as wavefront. So please write it down. So the definition of wavefront is locus of all points which are vibrating in the same phase. I'll come to them. You'll understand. When I draw the graph, you'll understand. As of now, have this in your. So it is, the definition is given here. See, a wavefront is defined as the continuous locus of all such particles of the medium which are vibrating the same phase at any instant. See, this definition is very, very, very important for me to see. Is it?
So, let us consider the same which is not. So, suppose this there's been C1, C2, the first lesson. So we consider the that part. So for that wave, should be the wave framing is same.
You're drawing a tangent, and I didn't say draw a tangent.
So the
Wavefront will not exist for the same wave. Wavefront will exist only for multiple.
so
Because one light source will not emit only one wave, it emits infinite number of waves. In those infinite number of waves, if you are able to choose all the points which are in the same phase, you call that kind particular shape as wavefront. Okay, shall I proceed? As discussed, a wavefront is defined as a continuous locus of all such particles. Such particles means those particles which are vibrating in the same phase of the medium, which are vibrating the same phase at any given instant. Means at any point of time, if you are able to collect those particles and join those particles, then the shape that you obtain is what is called as a wavefront. So if you take a wavefront, so basically wavefront is a shape, or to be more precise, I'll call it as a surface. So wavefront is a surface of constant phase. So if I have to give you an analogy of this, if you go back to the second chapter, there was something called as equipotential surface. So what is an equipotential surface? It's basically a shape on which every point is at the same potential. In a similar way, wavefront is a shape where every point on it is having the same phase. So equipotential, the same potential. Wavefront, it is having a constant phase. Now read the statement, it will make sense. Wavefront is basically what? It is a surface of constant phase. Means every point on it will have the same phase. Or I can say the phase difference between any two points on the surface is 0. Right? That is another way of defining. So if every particle is in the same phase, then if you take any two points and try to measure the difference between their phase, what will the answer be? 0. Is it not something similar to equipotential surface? And another important point to be noted here is the speed with which the wavefront moves outward. Remember, wavefront always moves in the outward direction. The speed with which the wavefront moves outward from the source is called the phase speed. Phase speed. Right on this part. The speed with which the wavefront moves outward from the source is called as the phase speed. Am I clear with this? Okay. Now I need to discuss the concept of the different types of wavefront, like how I told you. So the different types of wavefront, right? Like how I told you, wavefront is basically shape obtained by joining all the points in the same place. That depends on what kind of a source you are going to use. So depending on the type of the source that you're going to use, basically wavefronts are classified into 3 types, namely spherical, cylindrical, and the last one is actually a plane wavefront. There is a mistake. Okay. There is a repeated point. And the third is called as plane. It's called as plane wavefront. Okay. First, let us see one by one. Okay. So, what is a spherical wavefront? Suppose I have a point source. Right? I have a point source. And this point source, what it will do is, it will start emitting the light in all the directions. I call it as omnidirectional. Right? It starts emitting in all the directions in 3D. Right? So when this happens, can I say that the light is going to travel in the form of wave given? Right? So to put it in simple terms, can I say it is going to release multiple waves like this? It is going to release multiple waves. So if I take this as the first wave, for the first wave you have a crest. For the second wave you have a crest. Which crest am I talking about? The corresponding first crest. I'm talking about the corresponding crest. I'm not taking, if I take this as C1 and C2, I'm not talking about C1 here and C2 here. If I take C1 on the first wave, I should take C1 on the second wave also. If I take C1 on the third wave, if I take all such C1s and I try to join them, what shape am I getting? On a paper, it looks like a circle. But remember, light is getting emitted towards you and towards me as well. So when you take it in the 3 dimension, it looks like a sphere. That is why for a point source, light travels in the form of spherical waves. That's why we call them as spherical waves. I hope it makes sense. Right?
So, can a particle
called as coherent. Come to the point. Light coming from the same source is going to be coherent in nature. Right? Is it clear? So this is what we call it as, I hope you guys are writing it. This is what we call it as spherical wavefront. Going forward, I'll write wavefront as W. Which one you will consider? What will you consider? Okay.
So, if a body is vibrating, air resistance, so it slows down. But that time it's exhibiting waves of.
That can happen, but if you not compare it, so that requires a medium, right? So you're talking about damping for example, you talk about sound, you talk about the spin wave is vibrating. So light wave, when are you going to talk about damping? So when it is traveling from one medium to another, it is undergoing diffraction. Still it is in travel. So here we can discuss that. The next one is called a cylindrical wave. Means the wavefront will take the shape of a cylinder. Okay. If I have to give you a similarity of this, if you go back to the first chapter, in first chapter under applications of Gauss law, you have something called as a linear source. You remember? Right. So when we try to apply Gauss law for a point source, what kind of a Gaussian surface did we consider? Sphere. So for a point source, there it is Gaussian surface is a sphere. For a point source, the wavefront will be similar to it. It is similar. For a point source, it is going to be a spherical wave. Similarly, there what did we do? For a linear source, we considered a cylindrical Gaussian surface. Here, the shape that is going to get obtained will be a cylinder. How is it so? Let's ask. Suppose I say this is the linear source. Okay, let's say this whole thing is a light from which the brightness is coming out. Okay. The intensity is followed. Then this whole system consists of multiple point charges present on it. Right. So these multiple point charges are going to release multiple waves like this. Accept it. So to all these multiple waves, right? If I find the corresponding presses, see, I'm explaining with the help of press. It is not necessary that you need to be press. You can choose any other point also. So if I say this is a point where the phase is 2 pi by 3, right? This is the first phase. I'm considering a point where the phase is 2 pi by 3. On the second wave also, I need to consider that point where the phase is 2 pi by 3. Okay. When I join all these points, what shape do I get? I actually get straight line, right? Whereas when you see the light waves coming in this way, also, they come in this way, they go into the paper. When you join all those points, what shape do you get? You get the shape of a cylinder. Hence, cylindrical wavefront is observed for a light source which is linear in nature.
For that,
okay, now bottom will be happen. At the bottommost point, what will happen? The bottommost point source and the topmost point source. When you join all of them from the top, they look like a circle at the top and circle at the bottom.
what is also
Okay.
so
It will be like a hemispherical bowler. Right. So write it down. When the source of light is linear in shape, such as a fine rectangular slit, right? The wavefront is cylindrical in shape. This is because the locus of all such points which are equidistant to the linear source will be a cylinder. See, what you told is right. It should be like an hemispherical ball, but in general, what will happen is that kind of a shape is obtained only if you take the light and hold it like this. We don't do that. Generally, every light will have a casing. So it will have a casing like this. Right? So it does not go in the downward or the upward. And third kind of wavelength is called as plane wavelength. So what is the plane wavelength? Suppose the object is at infinity. Okay. Infinity means what according to physics? If it is at a greater distance, that's okay. Infinity doesn't mean literally infinity. Right? If it is at a greater distance where that object is behaving like a point object, though it has a finite size associated with it. Right? When you talk about the object placed at infinity, then how will the light source come out? They'll be flattened, right? Okay, I'll do one thing. About this plane wavefront alone, I'll explain after explaining the concept of rays so that you'll understand it better. Okay. So first point that we discussed is wavefront. The next concept that we need to discuss is ray. So ray is nothing but what you discussed in the previous chapter, ray optics. The only thing is we are going to see how a ray is supposed to be drawn for a wavefront. Okay. So basically, what is a ray? So ray is a one-dimensional shape which has a starting point but no ending point, right? So if you draw an arrow mark, okay, well, I'll stop with this. An arrow is basically called as a ray. But what does a ray have to do in this chapter? Is because we'll try to understand that. You're trying to draw the ray with respect to the shape of the wavefront. Okay. So again, I'll go back to the second chapter. You know what is an equipotential surface? The surface, the shape which is obtained by all the points which are at equal potential. So how is the shape of an equipotential surface and electric field? How is the electric field direction or the electric field line with respect to an equipotential surface? Is perpendicular, right? In a similar way, a ray is also perpendicular to a wavefront. Means if you know how the wavefront is there, if you want to draw the direction in which the light is traveling, you just need to draw a perpendicular to the wavefront at that point. That's the direction in which the light is getting propagated. Because wavefront is a shape. Shape will not talk anything about the direction. So you need somebody to tell you that this is the arrow mark or this is the direction in which light is traveling. For that, I need to take the help of a ray. So what we are doing is you're taking an arrow mark. Right? How is it drawn? It is drawn perpendicular to the wavefront. To do what? To represent the direction of propagation of wave. You're able to understand? So make a note of it. An arrow drawn perpendicular to a wavefront in the direction of propagation of a wave is called a ray. Okay. Write it down fast. Here. So as the name suggests, if it is able to represent the direction of propagation of wave, a ray of light also represents what? The path along with the light is traveling. It's an important point. Why do we draw rays? If somebody asks you on lunch, what is drawn to a wavefront to denote the direction of light wave? What will you say? The answer is the ray. Right? A ray of light represents the path along which light travels. Okay. Now comes an important point. I saw what is we discussed what is a wave, we discussed what is a wave, right? Now, what are the principles associated with it? So, rays are perpendicular to wavefronts, right? And the second important point is the time taken for light, I repeat it, the time taken for light to travel from one wavefront to another, okay, is going to be the same along any ray. I'll explain this point. Listen to this carefully. Suppose there is a point source this. These are the two concentric spheres. These are the two concentric spheres, okay? Now, when I take a ray which is drawn perpendicular, you understood how I do it perpendicular, right? So, what do I mean by perpendicular? At every point, I need to draw a tangent, and to the tangent, I need to draw a normal, right? So, when I do this, this becomes a ray perpendicular to the wavefront at every given point, right? Similarly, I'll be able to draw another ray also. Now, what they are trying to say is the time taken for the light to travel from one wavefront to another is going to be the same if you try to measure it along any ray. For example, if I take this scenario, I have drawn two rays. So, if I measure this distance or this distance, they will be the same. It's not radius, the distance between those two wavefronts, provided it is acting in the same medium. Because we know that speed of the light varies from medium to medium. You're able to understand what I'm trying to say? So, read the second point, the time taken for light. That is why they didn't mention anything about distance. The time taken for light to travel from one wavefront to another along any ray is going to be the same. It is a very, very important point. Make a note. There are often questions asked based on this. Clear? Suppose I talk about a plane wavefront. Okay. So plane wavefront is basically obtained for the repeated. Suppose I talk about a plane wavefront. So plane wavefront is basically drawn for the source which is placed at infinity. Okay. Because recollect the concept of rays. How are the rays with respect to wavefront? They are perpendicular. Have them in your mind. Okay. So in the case of plane wavefront, the rays are parallel. Why is it happening? Because for plane wavefront to occur, the object is placed at infinity. Where is it placed? At infinity. For the object which is placed at infinity, how are the set of rays going to be? Every set of parallel rays. So the set of parallel rays is what you technically call as beam of light. So for a set of parallel rays, if I have to draw a shape which is perpendicular to it, then what shape am I supposed to? I need to draw a plane wavefront. So this is something similar to the case of electric field. The Gauss law applied for calculating the electric field into a plane shape. It's a plane surface. So it's just a reverse. So I already know for the source which is at infinity, I have a set of parallel rays, and for the set of parallel rays, if I have to draw a wavefront, that wavefront will be perpendicular to it. Because wavefront needs to be perpendicular to a ray at every point. It's not like one point is perpendicular and not satisfied. That's not what the definition says. It should be perpendicular at every point. So then it should be a plane wavefront. That is why when you talk about the source which is placed at infinity, the wavefront that you obtain is a plane wavefront. Clear? Whereas when you talk about the point source, so when I talk about the point source, how will the wavefronts look like? So in this case, in the case of spherical wavefront, the rays either converge to a point or diverge from it. Suppose I give you a set of wavefronts like this. Okay, I'm asking you to draw the rays perpendicular to it. Then what you can do is you will draw the rays perpendicular so that what is happening to them? They all get converged at a particular point. Whereas if I give this kind of a shape, this kind of a system, I ask you to draw the rays, they all get diverged. So when you talk about the spherical wavelengths, the rays either converge or diverge from a point, whereas for a group of parallel rays, they are always a plane surface. Have this in your mind. This is an often asked one question. Okay. You can easily get it. It's very simple. Here, maybe no. But you don't use photon. You don't use photon because that also varies. When you talk about photon, right, you need to speak about its energy. If you recollect from chemistry, you know that energy of each photon is H2, where H is Planck's constant and U is the frequency. We generally don't talk here because this chapter we don't discuss about energy. But you can call it a derivation. Generally, it is of no use. So what did we discuss? We saw the introduction to ray optics, then we saw the concept of wavefronts and rays. So revise till here and come. Tomorrow's class will discuss something important. We'll get into the derivations. Okay. Those who are online, any doubt?
No, sir.
No, sir. No, sir.
Okay, we'll wind up.
Thank you.
Sir.
Thank you, sir.
Thank you, sir.